let's jump into one of our, I would say almost a long time members of things now. So Jonas, over to you at Gemit. Can you share your screen and take it from there?
Yeah, for sure.
Brilliant. Let's see that everything works. Excellent. So just take it away.
Very good. Good evening, everyone. I'm Jonas Bäckman, and I'm the founder and also the CEO of Gemit Solutions. What we do is we develop and deliver an industrial BI platform called eXecutive. And I don't like to call it a BI platform, but it is more like a PI platform, process intelligence, but it's more easier to explain it as an industrial BI platform. And today I will talk about two use cases. So this will be hardcore use cases with graphs and analytics. And it's two use cases from the water industry. So how you can use soft sensor or a virtual sensor to actually detect sensor instability and do that in a predictive maintenance context. So the first use case, we will talk about an oxygen sensor, which of course measures the amount of oxygen in wastewater in this case. And the sensor is connected to a SCADA system. That's a data acquisition and control system, typical industrial systems. And as you can see, it's a really a tough life to be an oxygen sensor in water like this. So why does a wastewater plant need oxygen sensors? To answer why, it is important to first talk about aeration in a basin. First, aeration is consuming a lot of energy, about 30 to 50% of the total energy consumption of a wastewater treatment plant, and that's a lot of energy. And if you do too much of air, that's not energy efficient, while too little air causes other problems. Unwanted microorganisms, foaming, and insufficient purification. And the control of aeration is in most cases handled by the SCADA system. Or in the biological stage, the cleaning is required regularly of the sensor, and you can understand that when you see the water. And also the measuring head of the sensor needs to be changed at certain intervals. So it's very important that the oxygen sensor measures correctly. Here you can actually see the signal from one oxygen sensor. And this is the data from one of our customers, and the data is from the customer SCADA system. In this case, the resolution is 1 hour, and we see the average value from each hour. So this is a historical trend. In eXecutive, it's possible to set the maximum and minimum values from each time step. So in this graph, we see the average, like the more dark blue, and the minimum and maximum values. And as you can see, we have some unwanted behavior here from the sensor, marked with a balloon here. So the big question here, can we somehow detect this in an easy way? Yes, we can do that. And in this platform, you can add an extra time series just with the maximum values. And that can be done with the calculator as shown in this slide. And after a couple of calculation steps where we end with a traditional moving average to remove signal spikes, we finally receive a very clear, like a shark fin. And the shark fin is our created soft sensor. If we rearrange a little bit here with the graphs, you can easily see that the shark fin corresponds to the unwanted behavior of the oxygen sensor. And now it's time also to set the alert level. You also see that in the graph. And this is done with, this is a normal person who actually can perform this. You don't need to be a PhD. So when the soft sensor value is equal to the alert level, the alert will be triggered. Simple. After the alert is triggered, Acre send out an SMS or email to the people in the send list. If alert is sent via email, you can also attach a report which shows the actual status. You see what's actually happened. And if it is needed, Acre can also send the information to the maintenance system to create, for example, an automatic work order. So what have we done so far? Basic analytics. Then we developed the soft sensor, the shark fan. And the last step, we set the alert level for the implementation. And then the soft sensor is ready for production in the background. And our customer implemented this solution on, I don't know, plus 10 oxygen sensor. I don't remember the total amount. We also added some other rules to the soft sensor, not only that I showed, but that was just to show the principle of how easy it is to implement soft sensor and put them in production. And I have a very short case number 2. And that's, this is the main thing in the case number 2. It's all about a polymer pump. And this polymer pump also is heavily used by the water industry. And polymer, it's a chemical used to remove water from sludge. And of course, pumps sometimes break. So the question is, we can create a soft sensor detecting strange behavior before it breaks down. So in this case, it differs a little bit from the first case. We have 2 different trends here. We have the frequency, and we have also the flow. And data is from the customer SCADA system in this case as well. And the yellow field, that's an annotation with the very important information that the pump breaks. And after some analysis, we end up with a soft sensor, which clearly also describes the problem when the flow and the frequency is not correlated. So in this case, alert is activated 2 weeks before the pump breaks down. And that's, of course, great for our customer who can make a planned change instead of a classic fire brigade call. So if I sum it up here, with this platform, you don't need any extra hardware to actually build soft sensor that detects strange behavior from the sensors. Use data you already have. And soft sensor can be used in many areas, like also for actuators and unwanted process behavior. And it's also use the same technique if you use machine learning algorithms. And this is the solution is very cost effective for the customer. And that is 8 minutes, Magnus.
You are so good at that, Jonas. Thank you so much.